So thank you, Liam, for that introduction. I feel like I should say a word about who you are, because we did not introduce you. So Liam Stanton was part of the Cimarron collaboration, and the work that I will talk about here was also done in the Cimarron collaboration, and it was part of work that Lauren talked about earlier. In particular, I'll be talking about the so-called buggered potentials, as Lauren referred to them as, and sort of what was the physical background for what we were doing. And actually, they're not completely just buggered potentials, but I'll get into that. And I also wanted to mention that Cimarron was where I first met John Castor. My role now in Design Physics Division was to basically be John's protege. Coming in from Quantum Simulations Group, I came in to learn about opacity and equation of state and how to provide some user support within what was then AX Division and now has become Design Physics Division. So I'm very happy to be here today, and I'm very honored to hear all of you speak today about your long history with John. It's been a real pleasure. So thank you very much to all of you for coming out and participating. So the Cimarron collaboration was a LDRD effort that was led by Frank Graziani, and the effort there was to develop a large-scale molecular dynamics code that was capable of addressing problems in plasma physics. So our starting point for Cimarron was this code called DDCMD, which is dynamically domain decomposed molecular dynamics, or something to that effect. The code had been initially developed to study dynamics in condensed phase systems. So it had been applied to tantalum solidification in particular. It was later applied to studying a Kelvin-Helmholtz instability between layers of liquid metals, and subsequently we applied it to plasma problems once we developed the capability to treat plasmas. It won 2 Gordon Bell prizes for the condensed matter work, and it was a finalist for a plasma heating problem that we did with DDCMD. So I think probably most people here are familiar with molecular dynamics, but the basic idea is that you put a bunch of particles in a box and let them move around according to Newton's laws of motion. So literally you're integrating F equals ma in order to calculate the trajectories of these particles. And the way that works is that you need a force law between the particles, and one common way of building up that force law is to assume that all of the particles interact via a pair interaction. That becomes problematic if you want to treat a plasma, because the interaction potentials between electrons and ions is singular because of the Coulomb interaction. Now, the thing that saves you in reality from everything just collapsing into some super dense state of matter that doesn't actually occur in the world here is that you have quantum mechanics. So the quantum properties of the electron actually keep it from just collapsing into the ion. Now, if you set up a molecular dynamics simulation naively with Coulomb potentials, it doesn't know anything about quantum mechanics. So our goal was to build statistical potentials that would essentially mock up the quantum mechanics in some way that gave us enough fidelity to treat high temperature problems, and I'll go into that. So the general approach here was that we would use statistical mechanics, quantum statistical mechanics, in order to develop an interaction potential, and then compare results from molecular dynamics simulations using those quantum statistical potentials to actual quantum calculations themselves, and in order to assess the fidelity of those potentials. And then, assuming that we were able to develop interaction potentials that were of high fidelity or high enough fidelity, we would then use those in dynamic problems, such as the electron-ion equilibration problem that Lauren talked about this morning. So the background behind the statistical potential is actually quantum statistical mechanics, as I said, and I apologize for the number of equations on this slide, but maybe in this audience I don't have to. So the basic premise here was starting from the quantum density matrix. So the idea here is that if all of the quantum states of a problem are known, then you can actually calculate thermodynamic properties using this thing called the quantum density matrix. And what this is, just to explain what this notation means, it's essentially saying, given some Boltzmann probability, what's the probability that a state could be existing in this state R prime, which is some configuration of positions and velocities. What's the probability that it could transition to this other state R? And that quantity is basically built up just from your quantum states with some Boltzmann weighting. Now the problem in reality is that for any problem that's bigger than a two-body problem, in practice we can't actually calculate the quantum state. We can't actually calculate psi. So it becomes impossible to calculate this density matrix analytically, but if you could then calculate the partition function from the trace of that density matrix, and you could calculate the expectation value of any thermodynamic observable from that density matrix as well. So path integral Monte Carlo is a way of making controlled approximations in order to actually sample the quantum density matrix. So the first approximation that gets made is that you take this operator, this density operator, e to the minus Hamiltonian over temperature, and you factorize it into a bunch of different steps along the configuration that moves your system from R prime to R. And that factorization is exact in the limit of infinite m. So if you can take m goes to infinity, then sorry, this becomes exact. I'm repeating myself now, but what this does is it gives you a quantity that you can actually sample using a standard Monte Carlo simulation. This is now, assuming that you can construct these individual probabilities, this is now a system of polymers or a system of particles where each particle is now represented by a bunch of points along a ring, and you can use Monte Carlo to sample the configurations of that system. Now, the other thing that's necessary here is that you have to calculate now these high temperature, so this now becomes an effective temperature that's now higher, and you can make certain approximations to calculate now this high temperature density matrix and relate it back to the temperature that you are actually interested in. A standard approximation that we use in path integral Monte Carlo is to construct this probability from the pair product approximation. So what we do there is we take this density matrix, we factorize it into a free particle term and a pair interaction term, essentially. And this pair interaction piece is what we actually use to calculate our statistical potentials. So that's why this is relevant to the molecular dynamics. So we take this, which I should also say, now that you're down to a pair density matrix, you can calculate that analytically for a spherical potential just by doing an expansion. So using the same kind of machinery that we use to calculate the pair density matrix for quantum Monte Carlo, we can now derive a statistical potential from that pair density matrix. So we calculate the pair density matrix from the exact solution of some two-body problem. In this case, it's an ion nucleus problem. And we then take the diagonal piece of that. So forget about R prime different from R. We're just going to take R equals R. That's locality. What that corresponds to in the path integral picture is that you take those spread out rings that represented your particles and you collapse them down to a single point. So now you've taken out the non-locality of quantum mechanics, but maybe that's okay when the thermal de Broglie wavelength is small because you're at very high temperature. So you throw out the off-diagonal pieces, and then if you take the ratio of this pair density matrix to the free particle density matrix, and then take the logarithm of that, then you can derive a statistical potential. And this is a plot that Lauren showed in his talk earlier that's showing what these statistical potentials actually look like for an electron-proton pair. Now, there was some work by the Germans many, many years ago, I think back in the 1960s, where Kelb actually had derived a similar form for this potential. And what we actually did was to take that form that Kelb derived and fit the statistical potentials that we calculated from the pair density matrix to this form, by using the thermal de Broglie wavelength and this parameter gamma that Kelb had in his equation as fitting parameters. So this gives you something that you can easily implement in the molecular dynamics code, and this indeed is one form of the so-called buggered potential that we used for the work that Lauren talked about earlier. Now, the other thing that you have to worry about with electrons is the Pauli exclusion principle. So the interesting thing about the Pauli exclusion principle is that it sort of says that two particles can't get within a certain radius of each other. Now, in a classical picture, you would think of that as an effective repulsion. And in fact, if you derive from the Fermi equation, or the Thomas Fermi equation, what an effective Pauli potential looks like, it indeed does look like an effective repulsion at short distance. And using this kind of Pauli potential, what we observed is that we could get good spatial distributions of electrons in plasmas when we compared to quantum calculations. But these potentials actually give fictitious forces at small r that introduce problems for dynamical simulations. So if you're trying to calculate thermal conductivity, for example, the electrons now have an effective repulsion that shouldn't be there, and that effective repulsion now is a mechanism for dispersion of energy, which actually lowers your thermal conductivity in a way that's non-physical and not at all what you were intending to do by trying to introduce this Pauli exclusion principle. The Pauli exclusion principle should actually decrease the cross-section for electron-electron collisions. In this case, we created something that increased the cross-section, but you need it to get the right spatial distribution. So it's sort of, it's interesting because it might be viable for, maybe you just want to calculate the local field corrections, you just want to know spatially where the electrons are, then the Pauli potential is a good thing. If you want to know about the dynamics, then it's a bad thing. So that was a problem we never completely solved. Okay, so having calculated these statistical potentials for hydrogen before we applied them to any kind of dynamical problem, our first task was to validate them using actual comparisons to full path integral Monte Carlo calculations of plasmas. So we simulated hydrogen plasma at different types of conditions. In this case, I'm showing some results for the pair correlation functions for proton-electron, proton-proton, and electron-electron pair correlation functions from the MD code using actually not the statistical potentials that I described, but a different set of statistical potentials, which is shown in blue. The path integral Monte Carlo, which is shown in red, except for the electrons, these green dots, you have like spin and opposite spin electron contribution. So you have two curves in the PIMC for the electrons. And then for the proton-proton pair correlation functions. The black curves here are from hypernetted chain calculations that John Castor did. And funny story here, I think that hypernetted chain code was actually the thing that led to a phrase that Liam first said, which was WWJCD, which is something that we often repeated. And what that meant was, what would John Castor do? And that's something I still ask myself on basically a daily basis, if not more than once a day. So what happened there was we got interested in HNC partly because we were comparing these calculations of PIMC, which were really expensive, to DDCMD, which was really expensive with a different set of potentials. And we said, well, gosh, sure would be nice if we could calculate those pair correlation functions without any noise and much faster. And it seemed like John went home over the weekend and came back with a fully working HNC code with results. And we're just like, wow, okay. So that was my Richard Klein / Lauren Benedict moment with John. Okay, and this is a plot Lauren showed earlier about temperature equilibration, so I'll just go on. Okay, so having applied these statistical potentials to just looking at what's a G of R, we wanted to study transport coefficients. So the ICF folks had told us, gosh, we really wish we knew the thermal conductivity better for hot, dense plasmas. And we said, well, gee, maybe we have a tool to address that problem. So let's try it. So what we did was we did a bunch of DDCMD calculations to calculate the thermal conductivity just using standard linear response, like one would use in MD to calculate transport. And then we compared those calculations to results from Purgatorio So what I'm showing here on the left is a calculation of electrical conductivity in hydrogen, and on the right, it's thermal conductivity in hydrogen. So the blue squares here are Purgatorio results. The purple squares here are quantum molecular dynamics results from Mike Desjardins at Sandia. And the black triangles are a Spitzer type of calculation with beam set to the Landau length. The red triangles are if we set beam to the thermal de Broglie wavelength, and that again goes back to the standard Coulomb logarithm formula that Lauren talked about this morning. So the interesting thing that we saw was that for the electrical conductivity, it looked like our classical MD with statistical potentials, but not including the Pauli interaction for the reasons that I stated earlier about why it messes up the dynamics, agreed well with Purgatorio. And the QMD was a little bit lower, but still same order of magnitude. This is percents difference, not like factors of 2 or 3. But when we compared the thermal conductivity, on the other hand, the classical MD looked much more discrepant. Now the scales on these plots are much different, so it looks like the agreement here is actually better than it was. Or actually, I'm sorry, this is the curve without the Pauli interaction. So I forgot I did not include the results with the Pauli interaction. With the Pauli interaction, the classical MD was like way down here. When we got rid of the Pauli interaction, it actually agreed pretty well with our calculations. And the thing that was interesting was that the DFTMD here tended to be higher. And the result of that work was that we actually traced that down to an issue with DFTMD. We think when you get to very high temperatures, the actual pairwise collisions of the electrons aren't properly accounted for in quantum molecular dynamics. You actually have to do something to account for those collisions. And that was work that Chris Scullard did. And here's a better plot of that. So for the thermal conductivity, basically we were comparing a bunch of quantum and classical Lenard-Bolescu calculations of the type that Lauren mentioned this morning with our various MD with QSPs and quantum calculations and DFTMD. And this is the main plot that I referred to a moment ago that I should focus on, which is that the original set of DFT-MD results we had was like a factor of 2 to 3 higher than the classical MD results, and that was in spite of the fact that the electrical conductivities were in good agreement. And the Purgatorio curve was here, just a little bit lower than the QSP-MD. The Lenard-Bolescu calculation came in here. And what we concluded from all of this after a lot of work on many people's parts was that these DFTMD points were actually the discrepant ones. But initially this made us really scratch our head about the QSPs. But in reality, it looked like they weren't actually that bad once you threw out the Pauli interaction. Now, whether that's completely justifiable or not is another question. But the main outcome of that was a new thermal conductivity model for the ICF program. Okay, so the thing that I discovered in the process of working on these quantum statistical potentials was that there was actually a really long history of doing this, even though when I initially heard about it, I thought it was something new and crazy, and why would anyone ever think an electron could be a classical particle? And one of the main papers I found that I thought was most useful was this paper by Barker in the Journal of Chemical Physics from 1971. One of the reasons I found this useful is that he was using an approach very similar to the one that I was using, and he, for hydrogen, had kind of mapped out where he thought the regions of validity of these potentials were. So that kind of became a starting point for me once I found that work. The thing that we had done that nobody else had done before was actually looked at higher Z elements, so higher than hydrogen. All the literature I found in the past was really focused on hydrogen. We applied the calculation that I talked about earlier for calculating the pair density matrix for many different values of Z and developed some fitting functions for those potentials to treat higher Z elements essentially in DDCMD. So one of the things that I've done recently is to dig out some of this QSP work due to some renewed interest in whether we could use this as a faster method to calculate equations of state for hot plasmas than path integral Monte Carlo, which is becoming more and more of a workhorse method, but which is limited really to only a couple of groups in the world that are doing it. So recently I've looked at carbon at a bunch of different densities and temperatures and calculated the internal energy and the pressure using DDCMD and made some comparisons with this model that was published in PhysRev-B. Now, the relevance of the model is that it's actually parametrized by quantum molecular dynamics and path integral Monte Carlo, in addition to experimental data. So it's really one of the best equation of state models for carbon that's out there, although we continue to refine our models all the time. So Barker had indicated that we needed to be at least 50% effectively ionized in order for the QSPs to be valid for hydrogen plasmas. And so based on that, I hypothesized that for higher Z, at least the L shell needs to be ionized, and it's sort of a question. So it's a question as to where this is actually valid for higher Z. Barker showed where it was valid for hydrogen. It's not clear when you have a bound K shell whether these QSPs would be valid at all or not, and that's part of my interest in looking at carbon. So what I found was that there were specific instances where the QSPs just failed. So this one that's highlighted in pink, this is an instance where the QSPs just failed completely. And one of the reasons you can tell that is the negative internal energy. That indicates that the system is bound. And when the system becomes bound, it becomes bound in unphysical ways, which I'll show in the next slide. But the thing that I found that was interesting here was that it's sort of hard to compare the internal energies because this model actually incorporates a shift based on solid state internal energy, and I wasn't sure how to incorporate that shift. So rather than focusing on that, I'd rather focus on the pressure comparisons. And the thing that I found that was interesting was that looking at a broad range of conditions for the 3.5 isochore going from 100 eV up to 1000 eV, and then looking at 10 grams per cc isochore at 1000 eV, the differences in pressure really are less than 10% in most instances. There was this one case where it looked like there was a bigger difference in the pressure, but we think that actually might have something to do with the fitting of the model in that regime and not so much anything that's happening with the QSPs. So based on this, it does look like there might be, this might be a fast way to calculate pressures for large arrays of phase space if one wanted to do so. But what I really wanted to sort out was when is this valid? And possible ways for determining the applicability would be to look at the 3/2 kT compared to the L shell ionization energy, what's the thermal de Broglie wavelength compared to the ion and or electron sphere radii, and what's the temperature compared to the Fermi temperature. So obviously we don't expect these to do well when the system is degenerate. So these are some examples of what the pair correlation functions look like. So on the left, I'm showing the 3.5 grams per cc calculation at 1000 eV. And then on the right, I'm showing carbon at 10 grams per cc and at 100 eV. Now, the calculation on the left went along just fine, and this green curve is the electron-carbon pair potential, and you see there's a strong correlation between the electrons and the ions, even at very high temperature. The electron-electron correlation function is pretty flat. The electrons are fairly weakly coupled. It decreases a little bit at small r due to the repulsion. And the carbon-carbon pair potential, of course, it's flat at large distance, and there's a large repulsion once you get into this sort of ion sphere radius where these electrons are gathering around the carbon atoms and making, there's a repulsion between the electrons, and there's the ion-ion repulsion that contributes to the shape of that curve there. For carbon at 10 grams per cc and 100 eV, on the other hand, what I saw was that we would get these pair correlation functions where you would get carbon-carbon solidification, essentially. So what I'm showing here are actually different time snapshots. The curves that have points on them are the curves for the carbon-electron pair correlation function, and the curves without points are the carbon-carbon pair correlation. So at the earliest time, there was already a peak starting to form in the carbon-carbon pair correlation function that I knew shouldn't be there, and it basically just increased as time goes on. And that is the evidence of essentially these classical clusters of electrons and ions forming that are just physically wrong and shouldn't be there. So we know that's bad. So when they fail big, which is great, in the sense that you know it's wrong when it's wrong. So the other thing that's interesting from this that you can get is you can get what does the density of electrons around a nucleus look like as a function of radius. And this, again, is an analogy with the types of things that we can look at using path integral Monte Carlo. So this purple curve is just a 1s core state for carbon. It plateaus at 2 because there's 2 electrons allowed to be in the K shell of carbon. All these other curves are different temperatures. So this green curve is actually that 100 eV case that I showed you failed. This blue curve is 120, which actually seemed to be relatively okay. 200 eV was definitely okay, 500 eV and 1000 eV. Part of the relevance of this plot is that when one of the questions as equation of state theorists that we often get is what is the Z effective for the plasma? The Z effective isn't a well-defined quantity to us because the electrons are defined by statistical ensemble. So the question of what is Z bar means that we have to define something about, well, at what distance are you concerned with Z bar at? And then for us, it's still an average quantity. So if I was to look at this in a dynamical sense, this quantity would actually vary as the system moves around. So I am running short of time, but the main thing that I think I determined here was that Barker's validity plot actually looks very much like the validity plot that I've constructed. So I'm just going to go forward one slide. So the points I'm showing here are simulations that I did that I determined did not fail, which are the black squares. This red line is a line corresponding to the L shell ionization energy divided by 3/2. And all these other points, the blue ones are calculations that I did that were close to the line and looked questionable, and the red ones were ones that were obvious failures. But if I look at Barker's plot, his region of validity is this area up here, and this is a degeneracy line here, which I'm showing as this blue line here. And it looks like I'm more or less agreeing with his assessment for hydrogen that it applies to higher Z. So at this stage, I'm looking at some other mixtures and other ions, but I will stop there. Thank you.